Okay, to continue from modifying this circuit of a 4-bit adder into a 4-bit adder subtractor, a 4-bit adder subtractor. Recall that what we need to do was add one mode control input, which would, here it is. What we need to do is add this mode control input M in a manner that when M is 1, it should subtract. When M is 0, it should add. We had seen the working of the XOR gate as a controlled inverter, where if one of the inputs A is considered as the mode input M, then the working can be analyzed as that when M is 0, the output is the same as the input B. B is 0, 0, B1, Y1. And when the mode input M is 1, these are the two conditions. In these two, if B is 0, Y is 1, B is 1, Y is 0. So we had analyzed this as when M is 0, Y is the same as B. And when the input M is 1, the output Y is the complement of B, which is nothing but minus B. The same can be translated in the circuit by using, or rather by adding, an XOR gate in the B input. Why are the XOR gates added in the B input, not in the A? Because the complement of B has to be taken. 1's complement of B and the 2's complement of B to give the negative representation of the number B as minus B. The same is realized in the circuit by adding XOR gates for each of the B inputs. And now we are left with adding the mode input M. So the second input of each of these XOR gates will be the mode input. So this is the second input of this gate, the second input of this, all the XOR, all these are connected together. The second inputs of the mode M, we call this as M, which is our mode input, connected as one input to each of the XOR gates. The other input of the XOR gate being the B input, and this will be called as the line M. And how will it perform the function of when M is 1, it should subtract? We saw that when M is 1 and the B is 0, 1 and 0 gives a 1. So this is the opposite of B. This will give and this you get as B0 bar. Similarly, if M is 1 here, this will give you B1 bar. If M is 1 here, this will give you B2 bar. If M is 1 here, you get a B3 bar over here, complement of B. Now to get this gives you the 1's complement of B. Now what about the 2's complement? The 2's complement is nothing but 1's complement plus 1. 2's complement is 1's complement plus 1. So where does this plus 1 come from? The same input M connected to the Cin. So when M is 1, Cin also will be 1. So the 1 will be entering from here. So this is the B3, B2, B1, B0 getting the complement, and this 1 getting here. So 1's complement plus 1. You're getting a minus B0, minus B1, minus B2, minus B3, minus by the 2's complement, this one. So this circuit will do nothing but A plus minus B, A plus minus B, A plus minus B, and A3 plus minus B3. Now, and when M is 0, so this performs the function of subtraction. Now let us see what will happen when M is, let me use another color for this. When M is 0, the circuit will add. Just try to visualize. If the M is 0 and the B0 is B0, 0 and 0 will give you a 0 here. So this will be B0 over here. If M is 0 and B1 is say 1, 0, 1 will give you a 1, which is nothing but the same. Similarly here, if M is 0, if you have B2 as 0, 0 and 0 will give you a 0. It's the same as B. And over here, if it is 0, if this is 1, 0 and 1 gives you a 1, which is the same as B. So in all the cases, you see that you get a same B over here. So what is happening is A plus B action is being performed, while in the first case, M is 1, the action being performed is A plus of minus B, where this minus B, remember, is the 2's complement. This minus B is your 2's complement of B. 2's complement. So you see that it is basically the 4-bit parallel adder which is modified to work as an adder subtractor. And to conclude our discussion, if you're asked to finally say or to finally answer that the 4-bit adder subtractor is implemented by using how many logic gates? So what are the number of logic gates used? Recall that the parallel adder had 20 gates. Remember? Remember that we had analyzed that in our previous class. In our previous class, we'd seen that the 4-bit parallel adder had 8 XORs, 8 ANDs, and 4 ORs, 20 logic gates. This was the circuit. And now if you compare this circuit with the 4-bit adder subtractor, if I am able to get them both in the same frame. No. So if this is the adder subtractor circuit, the additional number of gates are these 4 XOR gates. So the total number of gates in our adder subtractor are 20 of the full adder, parallel adder, and 4 more 24 logic gates. And what are those 24 logic gates? If you remember, I'll just put it over here. This was the 4-bit adder. So 8 XORs, this will have 8 plus these 4. 1, 2, 3, 4. So 8 plus 4, 12. So this circuit will have 12 XOR gates, and the other will be same, 8 ANDs, 4 OR gates. So this totals to 24 logic gates. I hope this is clear. 24 logic gates. So take a careful look at this circuit, this logic circuit. Rather, it is still a detailed block diagram. If you break it into logic gates, remember that this has 5 logic gates, this has 5, this has 5, and this has 5. So there are 5 plus 5 plus 5 plus 5, 20, plus these 4, 24 logic gates. So this is how 24 logic gates can be connected in this manner to perform the function of 4-bit addition, subtraction, and the circuit is called as the 4-bit adder subtractor. To summarize our class, let us just start from the beginning, which was the block diagram. We first saw the block diagram of the 4-bit parallel adder subtractor. It is a block which is similar to the parallel adder, adding two numbers, 4-bit number A and the 4-bit number B, giving you the 4-bit sum S3, S2, S1, S0, the carry out and the carry in. The only change was an additional input called as mode control input, labeled as M. If this is the external block diagram, and we saw the function of the XOR gate being used as a controlled inverter. Controlled meaning that if one of the inputs A is considered as a control input M, then the behavior of the XOR gate is analyzed that when M is 0, the output gives plus B, the same as B. So in this condition, the output is same as B. And when the mode is 1, M is 1, the Y is output is 1's complement of B, so that is minus B. If we remember the function of the XOR gate as a controlled inverter, then this is how the circuit modifies. 95% of the circuit being the same as that of the parallel adder. The modification for the adder subtractor is addition of these 4 XOR gates working as controlled inverters, the control input being M, mode control, working in this manner as M1 subtract A plus minus B, doing the process of addition each time. The process is addition A plus. When M is 0, again it is doing A plus B, A plus minus B. And finally we saw that the 4-bit adder subtractor is a combinational logic circuit implemented by using 24 logic gates, 12 XORs, 8 ANDs, 4 OR gates, all of these gates being 2 input gates. Thank you.